Hey folks, so today we're going to talk about circular functions and get a bit more into inverse circular functions. So if we're given y, we want to find x. Now keep in mind that this is actually really similar to inverse trig functions, which you've seen in geometry and algebra 2. Also keep in mind that these are circular functions. They come back to the same value again and again and again. Let's take a look at how all this gets thrown together. We're going to start off by looking at these four functions. We have cosine of pi over 3, cosine of 5 pi over 3, cosine of 7 pi over 3, and cosine of 11 pi over 3. Now, you can find all of these by just plugging into a calculator. And you're going to find something kind of funny. Cosine of pi over 3 is just going to be equal to 0.5. It's a half. Remember, pi over 3 is equal to 30 degrees, and you can kind of use special right triangles from there. Well, cosine of 5 pi over 3 is also equal to a half. Weird. Cosine of 7 pi over 3, well, if I plug that into my calculator, I'm also going to get equal to a half. Even weirder. And here, cosine of 11 pi over 3, if I plug that into my calculator, it's also equal to a half. Now, there are reasons for this. We would expect that these same values would pop up again and again because we know that cosine is a circular function. It's going to return to the same values again. Now, the difference between these two, the pi over 3 and the 7 pi over 3, is in between these two radians, we've just added 2 pi radians. Remember, that's a full cycle. So here we just went 360 degrees, we wound up in the same place. And the same thing happened here. This is just adding another 2 pi radians. If you're wondering how the heck is that adding 2 pi radians, it's because first, the 2 pi is going to be equal to 6 pi over 3, so that way the denominators are the same. And then the 1 pi plus a 6 pi is a 7. Similarly, in the second one, this is equal to 6 pi over 3, and I just do the 5 pi plus a 6 pi to get my 11 pi. Now, that brings us to an important statement. These all have the same value due to them all being solutions to this. We've seen in the past that you've used inverse cosine of a number and it just gave you a single number. But we're extending our knowledge of cosine and inverse cosine here. And we're trying to write a statement that gets us all of the solutions to this. Here's another way to think about it. We're going to think about them on a graph. I'm going to keep the numbers at the top there. Now, looking at this on a graph, we can see that our blue cosine function is always going to intersect our pink linear function here. Heck, it's intersecting here, 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 and here. And this is at pi over 3. This intersection is at 5 pi over 3. This intersection is at 7 pi over 3. This intersection is at 11 pi over 3. You can do much the same on Desmos, and you'll get where we're coming from. I want to draw your attention, though, to this negative one. This is happening at negative pi over 3, this intersection here. The reason I want to draw your attention to it is if I add my 6 pi over 3 here, add 6 pi over 3, well, negative 1 plus 6 is my positive 5. If I add my 6 pi over 3, I'm going to get my 5 plus 6, that's my 11. So each time I'm just adding 2 pi. I'm adding a full rotation. And I can write a statement that does this again and again and again and again and again. And in that manner, I'm going to be able to write out all of the answers. Similarly here, if I do my pi over 3 plus 6 pi over 3, I'm going to get my 7 pi over 3. Remember, all I'm doing is just adding a full rotation. Now we have a way to write this, and it's called arccosine. Let's take a look. Now this is something we call arccosine. It's called arccosine because it measures the arc of the unit circle. We abbreviate it like this, ARCCOS. Now it's different than cosine inverse. The reason being, cosine inverse returns one value. You've seen this in geometry when you're doing SOHCAHTOA. You plug cosine inverse of a number into your calculator and you just get back one number. Arccosine is returning all values, infinitely many. Just like we saw on our previous graph, we're trying to find every value that makes it true. And this is how it's defined. Arccosine of x is equal to plus or minus cosine inverse of x plus 2 pi n. Now this 2 pi you can also write as 360 degrees. So you could write this using degrees as arccosine of theta is equal to plus or minus cosine inverse of theta plus 360 degrees times n. N is always an integer. Basically, all this is saying is you find one answer to cosine inverse of x, and then you just keep adding on 2 pi. So you'll add on 2 pi, then 4 pi, then 6 pi, then 8 pi, and you'll constantly get answers. Now, the reason why this plus or minus is here, that's there because just like in our graph, we saw that if you went back a little bit to a negative answer, you could continue to add 360 to that. Let's see how this could be used when we're solving it or asking for a specific answer. So this is going to be from the problem set that you're doing for homework. You are going to be doing numbers 1 and 3, so you can check them in the back of the book. They're the odd questions. I'm going to show you an example with number 2. We're going to find the first 5 positive values of this circular relation here. Now we know that arccosine is going to be equal to positive and negative cosine inverse of 0.4 plus, we're going to stick with radians here, 2 pi times n. Remember, n is an integer. I'll show you how that is going to work in a second. Well, the first thing that we should probably do is figure out what this is. And for that, you can just use a calculator the same as you have in the past. Well, that means that this is going to be equal to plus or minus. I plugged that into my calculator, and I got 1.1592794.8 blah blah blah. Don't round yet. Really, don't round yet. It would be a bad idea. Plus 2 times n. Okay. It's also important to keep in mind something here. If you plug into a calculator that 2 pi, just plug that in. Well, 2 pi is about 6.28318531 blah blah blah. Okay? All I'm going to do here is do the positive, this red value, plus 2 pi times 1. That's one of my answers. Then the next is the positive red value plus 2 pi times 2. Then the positive red value plus 2 pi times 3. I can also find some other positive values by doing the negative red value plus 2 pi times 1. The negative red value plus 2 pi times 2. Let's see. So, okay. All I did here, I set it up, I just plugged into my phone's calculator. I didn't even need to use Desmos. I just plugged this in plus 2 pi, then this in plus 2 pi times 2. I actually just plugged in 4 pi. This plus 6 pi, or 2 pi times 3. I just rounded here at the end. These are the first 5 values that make this one true. Let's take a look at number 6. This one we're going to do all together. This is from your problem set, and you're going to be doing numbers 5 and 9 from the same problem set. I'm doing an even one. You guys are doing the odd ones. You're doing odd, so you can check your answers in the back of the book. So we have a graph here, and we're going to do 4 things. First, estimate graphically the x value shown in the indicated y value. Second, find a particular equation of the sinusoid. Third, find the x values in part A numerically. That means we're just going to check it. Fourth, find the x values in part A algebraically. So we're going to do part A first, strangely enough. So, and that we're just going to do by this. I'm just looking for where all of these values are intersecting. Same way that you've learned to solve systems of equations in the past. All I'm looking for are where the two graphs cross. That's happening at these values. Now, you might be saying, okay, well, how'd you get 0.5, 4.4? How are you so exact? Estimate it. It doesn't matter to me if you are off by 0.2 of a decimal. I mean, if you were going for 0.5 and you put -50, okay, that's a big error. Otherwise, this is fine. All we did was estimate the x values. Let's move on to part B. So B, we're going to find the particular equation of the sinusoid. Now that, we're just going to ignore the y equals 5, and we're just going to do all of these things the way we have been doing. First part, we go from 2 to 14 with the period. So that means our period is 12. Divide 12 by 2 pi, and then simplify to 6 over pi. Last but not least, we're inside the trig function, so we got to flip it. So instead of 6 over pi, it's pi over 6. Next, the amplitude. We're going from 7 to 1, and we just divide by 2. So max minus min divided by 2, our amplitude is 3. You can also check it using the graph once you have the midline. The midline is the max minus the amplitude, so here 7 minus 3, it's 4. You could also ask yourself, hey, what number is right in between 7 and 1? And that number is 4. Last but not least, the phase displacement. Our phase displacement here is 2. Reason being, here is where our graph is starting from. That's where a full cycle is starting. Throw it all together, and you get this equation right here. Same as we've done in the past. Part C. We're using the same equation that we just made. Only difference is we've put 5 into it. Now this 5 came from the y equals 5 up here. Because again, here we're looking for the x values, and we're just going to check them. So I'm going to plug in the same x values that we found in part A, the estimates. Well, here we're plugging in the x value of 0.5. That's the one that we got right here. And we get pretty darn close to it. That's okay. We can totally use that. So because we're really close, we get 5 is equal to 4.78, we can say, yeah, this one works. This is an intersection. This is an x value of an intersection. Next one, here we're plugging in 4.4. So we're using this intersection point right here, which is 4.4. And again, our estimate is pretty darn close. So we're just going to do the same thing with another one. And here we are using 11.6. 11.6 is happening right here. And we can see, yeah, we're pretty close here again. So because of this, this is checking numerically. You can tell that this is not algebraically because in none of this did we do algebra. We just plugged in the numbers, thus numerically. Speaking of algebra, let's look at this one. We're going to find all of these algebraically. And I like the purple one. I'm going to reuse the purple one. You guys know the main thing in algebra is inverse operations. All this is, no matter how wonky it looks. First things first, I subtracted 4 on both sides of it. This 4 disappeared, subtracted it to both sides. Second, I divided by 3. Remember, this 3 is attached to the entire trig function, so we can just divide by 3 on both sides, and we got rid of it on the trig function. Now, I'm going to take the inverse of both sides. You'll notice a slight difference from what you've done in the past with taking the inverse. Here I've applied arccosine as the inverse. That's because we're trying to find arccosine. Honestly, if you were to just write cosine inverse, I'd be perfectly fine with that. The only thing is, don't forget what we need to do at the end, using the definition of arccosine which we discussed before. So, next thing's next. I just multiply by the reciprocal of this fraction on both sides. You could also divide by the same fraction. It's the exact same thing as multiplying by the reciprocal. I bet you're all thinking what's coming next, and you'd be right. All we're going to do is add 2 to both sides here. Now x is finally by itself. That's great. This was all algebra, just inverse operations. Now we're going to apply what we just learned about arccosine by applying its definition. Remember, arccosine is equal to plus or minus cosine inverse plus 2 pi n. Here I'm using radians because we didn't have degrees up here. We started with pi over 6 as well, which is a really big giveaway that we're in radians. So I applied the definition of arccosine. Notice the things that changed. I have plus or minus here, I have cosine inverse here, and I have 2 pi n. That's going to be all from the definition of arccosine. Last but not least, I just distribute the fraction. I distributed this fraction from the previous one, and it's simplified over here to just 12n, pi canceled out. So perfectly fine. So you might be confused at this point. You might be thinking that you don't know what's going on. I assure you that you know more than you think you do. Right now, start that homework. You can skip the Q questions right now. You can come back to them later. That's fine. If you want to start with the ones that confused you most, okay, stick around on the call, ask questions about it. If you want to see another example, we can definitely do one as a class. But I'm here to help you. After that, do the reading. It's a really short reading, guys. And the summary. Have a great day, folks. I'm here to help.